Alright, physics. We left off here, right? And we were talking about how position time is connected to velocity time is connected to acceleration time as far as the graphs are concerned. And I talked a little bit about how this is a position time graph that represents some acceleration. And you should have noticed that it was different, not just because I used x instead of d. I'll try to use just d for distance, d for displacement. I'll try to be more consistent there. You should have noticed that these were all straight lines, but this one was curved, right? Hopefully you make that connection. Hopefully I mentioned this in class, but if the position time graph, if the distance time graph is curved, if there's a curve to it, it means that there's some kind of acceleration going on. It means that the velocity of our object is somehow changing, right? And what I'd like to do here now is just pin down the different ways that you will see that the distance time graph displays acceleration. Because you'll be asked to you will be asked to interpret this very soon in your quiz. Now I said quiz before. It's really going to be more of a lab exercise. You're going to do a lab, you're going to take some numbers, you're going to evaluate the numbers, and then you're going to compare what you see in your numbers, and if you potentially made a graph, compare that to another set of data and see any similarities or any differences. Alright? Here we go. So what I'm going to do is I'm going to break down a few distance time graphs that represent acceleration, and how they represent acceleration, and physically what you would observe, what you would see. Alright? So let's do it. Now, the first one... Ooh, let me be fancy. So I know that the scrolling is loud. I'm working on a little bit of noise canceling for that. It's a work in progress. Hopefully, again, hashtag soon, I will have a better feel for how all that works. Audio, sound engineering, and all this kind of production is not exactly my forte. I'm learning this as I go. So, here we are. Let me make these just slightly longer than they are. So we're going to pretend that's all one continuous straight line, just like we're going to pretend that this is all one continuous straight line. Okay. The only reason I made these longer is so that I don't have to do 4, I can just do 2. Right. So what I'm going to do is I'm going to do this. And I'm going to make this distance in meters. I'm going to make this time in seconds. I'm going to do the same thing. This is going to be distance in meters. This is going to be time in seconds. This inverse version of the parabola is always difficult for me. Yeah, we're going to pretend that's good enough. That's good enough. It's not. It's not. It's not good enough. Never settle, kids. Oh my gosh. What? Fine. I'm going to settle. It's taking too long. I don't want to take too much time. So these are both displacement time. I'm going to focus on the top one first. What is happening? I'm actually going to split this graph kind of in half. Split it right there. And I'm going to analyze this first section up here. So if we look at this, right here, we have a slope that kind of looks like this. And as you follow the curve, as I follow it to its peak, now we can move it. the slope goes like this, and it curves out, and it flattens, which means the slope has some kind of positive value at first, and it has less positive, less positive, less positive, and eventually it's 0. Now, if you remember, I think I said this in class. It's just not how you spell slope. If you remember, the slope... okay, this is where I'm running into a problem. There we go. The slope of the distance time graph tells you velocity. So if the slope is positive, it's a positive velocity, and then as it gets closer to 0, the velocity is 0, which means that this section is moving forwards because it's going from low to high. Right. And it's slowing down because it's positive slope to 0 slope. Right. Which means so we're moving forward, we're slowing down, positive slope to 0 slope. This section, and I'm pointing only at, like, it might look like this arrow is only pointing here, but I'm really pointing for this whole second half. The slope is 0, and then it goes this way. It gets more negative as the slope happens, and so this tells me two things. This motion tells me two things. This is moving backwards, or high to low, and speeding up because it's 0 slope to negative slope, right? But if you look at it, there's an object moving forward. I say forwards because it's just going positive. I tend to think of things in the forwards backwards axis of motion. It's just like the simplest thing for my head to latch onto, like walking forwards, walking backwards. So it seems very straightforward to me. There's an object that's moving forwards because its position is going from low to high, right? Its position is getting more positive, so we're moving forwards. And we're slowing down because we're covering less and less distance in each time interval, or you could say that the slope is getting closer to 0. After this point, the slope starts at 0 and it gets more negative, so we're speeding up because we had 0 velocity. If the slope is velocity and the slope was 0 and then it has a value, the slope is speeding up, or the slope is getting more negative, so we're speeding up. We're going backwards because we're going from a high to low, right? Our position is getting more negative. Similarly, down here, I can do something similar. Again, I can kind of split this down the middle-ish, and I can look at this section. This has a big negative slope. Sorry, has a big negative slope, and it evens out to 0. This is moving backwards again because it's going high to low, and it's slowing down because, look at the slope. This slope in the first half is getting closer to 0. Now, I know I didn't draw a perfect graph. I can only do so much. But it's a negative slope to, let's draw a better number, 0, to 0 slope, right? And then here, we're moving forwards. This is low to high, and speeding up because it's 0 slope to a positive slope. Right? Now, both of these graphs show us some kind of acceleration. I will tell you that both of these scenarios are a negative acceleration, and both of these scenarios are a positive acceleration. Right? So both of these are negative acceleration. When you're moving forwards and your acceleration is negative, right? If you're moving forwards, by the way, just another little note here. Moving forward means positive velocity, right? Try to think back to last year to chemistry. Whenever you had one rule, there was almost always the opposite rule for it. So if moving forwards is a positive velocity, then moving backwards means negative velocity. That's not just not how you spell velocity. Let me do a better job. The reason I bring this up, when we're moving forwards here, we had a positive velocity and a negative acceleration. We're moving forwards, but there's a negative acceleration. There's something that's trying to like pull us backwards while we move forwards, which means that our speed, right, we're slowing down. Then when we were moving backwards and there was a negative acceleration, so we're moving backwards and something is pulling us backwards, we start to speed up. The opposite thing happens here. We're moving backwards, but there's a positive acceleration. So we're going backwards, something's trying to pull us forwards. We're slowing down. Once we start physically moving forwards and something is trying to pull us forwards, we're speeding up. Right? These four graph shapes, are how to tell based on the distance graph that you have an acceleration. Now I bring it up for distance graphs because on a velocity graph it'll be very obvious if there's an acceleration. If velocity is changing, you have acceleration. It's less obvious here because distance graphs, distance time graphs, displacement time graphs, they don't tell you velocity outright. You have to do a little bit of analyzing. They tell you where you are. If you see a curved shape on the displacement time, on the distance time graph, that means you have an acceleration. If it's a sad face, right? Frowny. That means your acceleration is negative, and it might seem silly, but that's a connection you can make. If the shape of your graph is a frowny face, if it's a frown, that means you have a negative acceleration. Now that's true even if you can only see, half the graph. This is half of a frown. It's still negative acceleration, right? This half is still half a frown. It's negative acceleration. If you have the happy face, right? If your parabola faces upwards, then it's a positive acceleration. Smile, right? Smiling, positive, frowning, negative. That's how you can tell based on the graph what your acceleration is going to be. So later, if you do math, you can kind of check yourself. You can check your math with the picture that you see. All right? Now, you'll be doing some of this interpretation on your lab/quiz. I don't know how I'm going to call it, but it's total point, so it won't really matter. But you'll have to do some interpretation based on this and based on your own numbers. We'll compare and contrast. If you have questions, please bring them in for F-Day. That way I know kind of like where to steer myself. Otherwise, I'm just going to say stuff, and if I say stuff that you already know, you're going to be bored. I prefer not to do that. So anyway, in any case, keep track of this. These notes are on my CBA. Like, my version of this is on my CBA. It's a touch neater, but no matter what, it's here. It's there. We'll talk about it. I'll see you in class. Take Take care, kids.